Our life is embedded with a lot of mathematical functions, which we generally don't realize. But almost every basic math function we know is defined for all real values, which is negative infinity to infinity. So, what is infinity? Is it a number? Or is it an expression? Infinity is something we cannot wrap our minds around. It's something we possibly cannot understand, and we just make assumptions about it. Infinity behaves strangely. Sometimes, infinity times 0 tends to 1, and at times 1 raised to infinity tends to the constant e. We can't think of it as a number, since it is a concept used to represent something boundless. Now, for example, let's consider this question. 1 upon x squared dx integrated from -3 to 2. How will you solve this? Feel free to pause the video and try it out yourself. If your approach was this, then unfortunately it's wrong because the function is not defined at 0. Now, the right way to approach this is given below. Since infinity is something we don't understand, we cannot equate infinity minus infinity to 0. Therefore, the right answer is not defined. We cannot avoid infinity while solving actual problems, since we use functions like sin t when representing an AC voltage source, as time t ranges from 0 to infinity. We end up making assumptions that create a lot of difficulties while dealing with such functions. Hence, we need a way to alter our domain. Let's consider a function, the absolute value of t. It is defined over 0 to infinity. So, if we wish to eliminate infinity, we can assume the function t to be equal to 1 upon x. So when t tends to infinity, x will be equal to 0. But at t equals 0, x will tend to infinity. So we couldn't successfully eliminate infinity. Now, if we were to take u equals e raised to minus t, when t equals 0, u equals 1. And when t tends to infinity, u equals 0. So we converted the limit from 0 to infinity to 1 to 0. Similarly, a successful way to deal with such functions is by implementing Laplace transformation. So if we have a function f of t, we can alter its domain by operating on it as such. By applying the Laplace transformation, we will have successfully eliminated infinity from the function's domain and converted a function defined over the time domain to its corresponding frequency s domain function. Let's dive deeper with some application. We use Laplace transform to convert complex differential equations to relatively simple equations having polynomials, since polynomials are fairly easy to solve. A simple Laplace transform is conducted while sending signals over any two-way communication medium, such as FM/AM stereos and cellular phones. When information is sent over a medium such as cellular phones, they are first converted into time-varying waves, and then it is superimposed on the medium. In this way, the information propagates. Now, at the receiving end, to decipher the information being sent, medium wave time functions are converted to frequency functions. Here are some real-time applications. Number 1. Analysis of electronic circuits. Laplace transform is widely used by electronic engineers to solve differential equations occurring in the analysis of electronic circuits quickly. Number 2. Nuclear physics. In order to get the true form of radioactive decay, a Laplace transform is used. It makes it easy to study the analytic part of nuclear physics. Number 3. Data mining. Machine learning focuses on prediction, which is based on known properties learned from the training data. Data mining focuses on the discovery of unknown properties of data, where Laplace transform is used to determine the prediction and to analyze the step of knowledge in database. And number 4, Laplace transform to solve differential equations. An ordinary differential equation can be easily solved by the Laplace transform method without finding the general solution and the arbitrary constants.